Hey everyone, welcome to this explainer. We're going to dive right into one of the absolute most frustrating, time-consuming issues you can ever face in the lab, reagent lot-to-lot variability. If you've ever been perfectly on track for an assay validation only to have the wheels completely fall off because a new, supposedly identical bottle of antibody arrived, well, you are in exactly the right place. Today, we're going to decode why this happens and, more importantly, how to fix it.
So if assay drift is stressing you out, don't sweat it. We've got a really clear 5-step game plan today. We'll be covering when stable assays drift, how to triage before you troubleshoot, diagnosing assay failure patterns, solving drift with DOE, and finally building bulletproof assays.
All right, Section 1, when stable assays drift. Let's kick things off with a scenario that literally every assay development team knows a little too well.
Picture this. You ran an assay last week. It was perfectly stable. The data looked absolutely beautiful. But today the exact same method looks completely out of whack. It's making you question the entire run, and honestly, maybe even your own sanity. It's the worst feeling in the world, especially when you're staring down a tight deadline.
You do a little digging and trace it back, and boom, there it is. A brand new lot of reagent was opened. Maybe it's a new capture antibody, a blocker, or a calibrator. Suddenly your standard curves are shifting all over the place, your sample recovery changes, and your precision just widens out. Panic sets in, mostly because this always seems to happen right when a method is practically ready for validation. It is without a doubt one of the most expensive kinds of variability a lab can face.
Now when that panic hits, it's so tempting to just blindly guess the cause, right? You tweak an incubation time, run a plate, change a wash step, run another plate. But listen, this ad hoc troubleshooting, it's a fast track to nowhere. You're just wasting time and completely exhausting your resources. Instead of that panic-driven, one-at-a-time tweaking, we need to pivot towards structured lot qualification. That means planned comparability. We have to test systematically.
And we absolutely have to do this because regulatory bodies are watching closely. The FDA and ICH M10 guidelines actually agree that same reagent, new lot does not mean same assay behavior. We're dealing with critical biological materials here. Their performance is going to shift. That's exactly why lot changes must be handled as planned comparability exercises, not after-the-fact frantic investigations.
Which brings us to Section 2, triage before you troubleshoot. Before you go tearing your entire method apart, take a breath. We need to confirm that this lot change is actually the real isolated problem.
Our first instinct is usually to just blame the newest reagent right out of the gate. But stop right there. We need to follow a strict triage checklist. First, confirm exactly what material changed. Was it just the detection antibody? Next, look for other simultaneous changes. Are you absolutely sure it's not an instrument maintenance issue, or a different analyst, or maybe a temperature deviation that just happened to coincide with the new lot? You gotta rule that out. Then, review the historical performance, not just the one plate that failed. And please, avoid relying on a single summary metric that just says the run failed. Dig into those raw signals. The strongest labs treat these shifts like mini bridging studies. Step 1. Define what success looks like before you even start testing. Predefine those acceptance criteria. Step 2. Use a really smart sample panel. Don't just throw in a few mid-range controls. You want low, mid, and high concentrations, plus some tricky interference-prone matrices. Step 3, run the old and new lots side by side in the exact same experiment. Keep the analyst and instrument constant. And Step 4, separate the bias from the noise. You need enough replication to know what's a true systematic bias versus just normal everyday assay noise.
Moving right along to Section 3, diagnosing assay failure patterns. Okay, so you've got your data from the mini bridging study. Let's map out what those failure patterns are actually trying to tell you.
I love this because we should treat assay troubleshooting exactly like medical triage. Different diagnostic symptoms point to completely different root causes. For example, if your standard curve shifts but the controls still pass, you're probably looking at a calibration shift that's just hiding inside really wide QC limits. If controls drift all in one direction, that points to altered reagent potency or a matrix interaction. What if recovery only gets worse in specific matrices, like say lipemic samples? That means the new lot is interacting differently with those specific components. And here's a really fascinating one. If your precision just gets worse overall, it doesn't automatically mean the new reagent is bad. Actually, it often means the new lot simply exposed a pre-existing robustness weakness in your assay that was always there, just waiting to strike.
All right, Section 4, Solving Drift with DOE. When those simple yes or no lot comparisons don't give us a usable assay, we need a significantly better tool to fix the drift.
The crucial shift here is getting away from that one factor at a time guesswork. We need to introduce design of experiments, or DOE. If you're new to this, think of DOE like testing an entire recipe all at once, instead of swapping out single ingredients one by one and just crossing your fingers. It's a structured methodology that lets you test multiple assay variables simultaneously to see exactly how they interact with each other and with that tricky new reagent lot.
So instead of running one plate just for incubation time, and then a whole separate one for temperature, a structured DOE lets you immediately see how the new lot interacts with multiple factors all at once. You can test incubation time, wash stringency, temperature, antibody concentration, and blocker composition together. This is a real game changer because it reveals the hidden interactions between these variables. It shows you exactly what combinations actually control the difference in performance rather than just what you guess might be controlling it.
And by using DOE, you aren't just applying a temporary band-aid to a drifting assay. You're actively finding your robust operating space. Basically, that's a sweet spot, a window of assay settings that is forgiving enough to survive an analyst swapping out, typical daily lab reality, and most importantly, future reagent lot switches. You stop hoping the assay works, and you scientifically prove the exact boundaries where it is guaranteed to work.
Let's move to our final section, Section 5, Building Bulletproof Assays. Because ultimately, we want to stop fighting these fires and start preventing them entirely.
The absolute best long-term fix isn't getting faster at your fire drills, it's establishing much better change control. First off, you've got to maintain a critical reagent register. Keep track of those lot numbers, storage history, and past failure patterns. Why make the next scientist rediscover all of that from scratch? Crucially, always keep a reserve inventory of your outgoing lots so you can actually run true side-by-side bridging studies. Oh, and get those standard sample panels established way before a crisis ever hits the lab.
At the end of the day, lot-to-lot variability isn't just an annoying procurement headache. It's a massive method control problem. So I want to leave you with this. Take a hard look at your lab's current methods. Ask yourself right now, are your assays truly robust? Are they scientifically defined by tools like DOE? Or are you honestly just waiting for the next reagent lot to fail, derailing your lab and halting your validation? Thanks for joining this explainer, and I really hope this structured approach helps you finally take back control of your assays.